Good morning, good afternoon, good evening. MSM3, we are talking today about exponent rules, part 1. We're going to talk about a few different exponent rules today and in the next lesson. And you'll notice that I'm going to use some highlighter, and that may help you at some times. So if you don't already have something to write with or highlight with, you may want to pause this and grab some highlighters. First of all, we're going to explore rule number 1, product of powers rule. So what happens when you are trying to multiply things that have an exponent? So this one says a to the m times a to the n. And in order to simplify that, you'll notice they both have an a for the base, and we combine the exponents by adding them. So if the bases are the same, x to the fourth times x to the fifth, you'll notice it's a product multiplication. We would get x to the, and the power would be 9. We would add the 4 and the 5 together. 2 to the second times 2 to the third. The bases are both 2, so we would get 2 to the, and we would add the exponents together for a 5 exponent. X to the negative fifth times x to the fourth. So we're adding the exponents negative 5 and 4 together. More negatives than positives, so it's a negative 1. So it would be x to the negative first. Same idea, y to the negative sixth times y to the negative third. I'm going to add the exponents negative 6 and negative 3 together for y to the negative ninth. Z to the negative 10th times z to the 16th. Negative 10 plus 16 would be z to the 6th. Now, if you have more than one, you simply add them all together. But this last one is the one that sometimes catches people. It's an x, and it has no exponent. Well, it actually does. It's an x to the first. And we don't usually write it because we don't need it. It's just 1x. But when we're going to add all those exponents together, we have to add the 4 and the 6 and the 1 to get x to the 11th. Here, we can combine, again, ones that have the same base. So x to the fourth times x to the ninth, that's going to be x to the 13th. Y to the second times y to the fifth, that's going to be y to the 7th. And they're being multiplied. I don't need to put the dot. It's x to the 13th times y to the 7th. They are being multiplied, but if I don't put a dot, we still assume that it's multiplication. Last but not least, if you have a number raised to an exponent, that 4 to the third means 4 times 4 times 4, which we can do. It is 64. Then we can simplify y to the fifth, z to the 7th, and say, oh, geez, they don't have the same base. So I would write y to the 5th, z to the 7th, and I cannot combine them since the base is different. That's as much as I can do is just the 4 to the 3rd. Now, if we go to rule number 2, it says quotient of powers rule. Now, we know that quotient means the answer to a division problem. So all of these are going to be when we divide things with exponents. So first off, we have a to the m over a to the n. You'll notice we do a to the m minus n. We subtract the exponents. So if we look really quickly, product of powers rule, we add the exponents. On quotient, we subtract the exponents. So here I took the m, which was the one in the numerator, and subtracted the n, which was the exponent in the denominator. We're going to continue that pattern. C to the x over c to the y. C is the common base, and I'm going to do x minus y. Since I have no idea what x minus y is worth, I'm just going to write x minus y. I've got x to the fourth over x to the negative 7th. Now, this is asking me to do 4 take away negative 7. Or 4 plus a positive 7. So the bases are the same, x, 7, 8, 9, 10, 11. It would be x to the 11th. I am subtracting the exponents, but since this is subtraction of integers, I rewrote it as addition first. Same idea on this one, negative 3 in the numerator, take away 5 in the denominator. I can rewrite that as negative 3 plus negative 5. It's going to be y to the negative 8th. That is a negative 8, even though it's missing the little holes in the 8. 5 to the negative 8 over 5 to the negative 4th. So I'm going to do negative 8, take away negative 4, rewrite that as addition, negative 8 plus a positive 4, and I would get 5 more negatives than positives, 5 to the negative 4th. This one's a little easier. 7 take away 5 would leave us with 7 to the 2nd. Now here's where I said I was going to use some highlighters. I'm going to make sure that I'm only simplifying things with the same base. So I've got x to the 10th over x to the 4th, and those have the same base. And then I've got a y to the 4th over y. Those have the same base. And then I have a z to the 3rd over z to the 2nd with the same base. And I'm going to do the same process of subtracting the exponents, just one at a time. So x to the 10th over x to the 4th is x. 10 take away 4 is to the 6th. Y to the 4th over y is really y to the 4th over y to the 1st. So when I subtract those, I get y to the 3rd. And z to the 3rd over z to the 2nd is z to the 1st. And you'll notice that I don't write the exponent. I just put a single z. Same idea, moving forward, I'm going to look and see what has the same base. A to the 5th over a to the 2nd. I also have a c to the 9th over c to the 3rd. But the b does not have sort of a partner in the denominator. So I don't highlight it. It just ends up being part of my answer because there's nothing to simplify. So a, 5 take away 2 would be a to the 3rd. I cannot simplify the b to the 3rd, so I'm just going to leave it b to the 3rd. And c to the 9th, c to the 3rd. If I do 9 take away 3, I have c to the 6th. So always making sure that I am simplifying ones that have the same base. Now, this last one is a little bit different because I've got two things in the numerator with an a over an a to the 2nd, and then I've got my c's. So if it were me, I would simplify the a's first, a to the 5th, a to the 3rd. They're being multiplied. They're worth a to the 8th, c to the 9th over a to the 2nd, c to the 3rd. The only thing I did was simplify these two a's that were being multiplied. And then I would look and say, can I simplify a to the 8th over a to the 2nd? Can I simplify c to the 9th over c to the 3rd? Sure. 8 take away 2 gives me a to the 6th. 9 take away 3 gives me c to the 6th. So it's not terribly difficult. Do have to remember our adding and subtracting integers rules. Next one is zero exponents. So rule number 3, I'll change my color here. B to the 0 equals 1. The rule, anything to the 0 power is equal to 1 all the time, always. Anything to the 0 power. So in this case, you're going to see me ask you for y to the 0. Anything to the 0 power is worth 1. 9 to the 0, anything to the 0 power is worth 1. 1.92 to the 0, still worth 1. 934 to the 0, still worth 1. That is a pretty straightforward rule. Rule number 4, our final rule in this set of notes, negative exponents. This is the one that you may want to rewatch. Anytime you have something to a negative exponent, it is the same as dropping that base with the exponent into the denominator with the opposite sign. So I can say b to the negative n, or I can put it 1 over b, and you'll notice that the n becomes positive. So let's just look at this a few times. 4 to the negative 3rd is 1 over 4 to the positive 3rd. By dropping it into the denominator, the exponent became its opposite. 2 to the negative 5th, 1 over 2, the negative 5th becomes a positive 5th. X to the negative 4, 1 over the negative 4 becomes an x to the positive 4 in the denominator. Y to the negative 8th becomes 1 over y, the negative 8 becomes its opposite, positive 8. Now, why is there always a 1 in the numerator? Because there's nothing left in the numerator when this drops to the denominator. But here, on this example, there is a number that is not raised to the negative exponent. That 3 sitting out in the front is not raised to the negative 7. So when I put the y to the 7th in the denominator, the 3 stays in the numerator because it didn't move. On this one, when the x to the negative 2nd drops to x to the 2nd in the denominator, the 12 stays right where it is. It is not raised to the negative exponent, so it stays in the numerator. Last but not least, we just have this one where it's sort of a mix of a little bit of everything. This first one you'll notice is all multiplication. So I'm looking for anything that has the same base. I've got an x to the 4th and an x to the 2nd. Those will be able to be combined. I also have a y to the 3rd and a y to the 2nd that can be combined. Remember, when it's multiplication, you add the exponents. So I have a 7 sort of hanging around with nothing to mix with. X to the 4th, x to the 2nd. If I add those exponents together, I get x to the 6th. Y to the 3rd, y to the 2nd. When I add those exponents together, I get y to the 5th. Now, if you want to ask, why are you adding the exponents together? Well, x to the fourth really means x times x times x times x times your x to the second, which is another x times x. Altogether, there's your x to the sixth. The second one, y to the third, times y to the second. If you write it out, you'll notice you have y to the fifth. So there is a reason behind why we are adding the exponents together. Now this one, you'll notice there's a whole bunch of stuff, but on the outside of all this stuff in the brackets is being raised to the 0 power. That means everything in the brackets raised to the 0 power is worth 1. That's it. No need to do extra work. Last but not least, this is going to still follow order of operations. I'm going to do everything in the numerator first. So 5 times 4, 20. X to the seventh times x to the negative third. I'm going to add those exponents together for x to the fourth. Y to the third, nothing to combine it with, so it's just going to stay y to the third. I have nothing to do in the denominator, so I'm going to just copy it over. Now I'm looking for things that have a common base. So y to the third and y to the second have a common base. But you'll notice you also have a 20 and a 2. They can be simplified as well. So let's think. 20 divided by 2, that's a fraction bar, right? 20 divided by 2 is 10. X to the fourth has nothing to simplify with, so it just stays x to the fourth. Y to the third over y to the second. If I subtract 3, take away 2, I get y to the first, but all I do is write the y. All right, so we are going to do a lot of practice on rules 1 through 4 of exponents.